that you have reversible reactions. Firstly, I'm just going to go over whatever that has been done in O levels. You have reversible reactions, reactions that can go in forward and backward directions. One example of a reversible reaction, not all reactions are reversible. One example is like a change of state. That's a reversible reaction. Liquid water can change into water vapors in gaseous steam and vice versa. So that's a reversible reaction. That's a process. And reversible, when we talk about reversible reactions, what we actually mean is we want the reactions to reverse at the same time. That like they can go forward and they can go backward and they can do it pretty much at the same time. For example, I mean, there are lots of processes that are reversible in the long run, like uh, like you burn wood and carbon dioxide gas is produced. That carbon dioxide gas gets uh, it is again photosynthesized, and when photosynthesis happen and wood is found back again. So that's kind of a long-term reversible process. So we're not talking about long-term reversible process, things that can happen and go forward and backward at pretty much the same time. So here's one reaction. Not a lot of reactions are reversible. Uh, so liquid water changes into gaseous water vapors. Uh, so let's think of a container, and you have liquid water in it. So there is H2O in liquid state. Now, what would happen? What's going to happen is, let's say there is no water vapor right now. So, and you have lots and lots of liquid water molecules. Now, the first thing that would happen is that some of the water molecules would gain energy and they would start to evaporate. So you have a closed system. Reversible reactions always happen. Equilibriums are always set up in closed systems. So there's liquid water. This molecule, let's say, becomes very energetic. It escapes as a gaseous water vapor. So right now, the reaction is only happening in one direction, right? It's going in one direction. Liquid water changing into gaseous water vapors. Similarly, there's another water molecule. It becomes energetic. Another one gains energy after collision and it evaporates. And so more and more water molecules would evaporate. But this process would not go endlessly because eventually what would happen or what would start happening is that these molecules would also bump into the walls of the container and they might lose energy. And when they lose energy, they're going to condense back again. So a reversible process would be set up. And if every second five molecules evaporate, let's say every second five molecules evaporate, but in the same, or let's say three molecules evaporate, but at the same time, three molecules lose energy and they condense back again. The net number of molecules would remain exactly the same. There's not going to be any net change in the amount of particles that are present in gaseous state or in liquid state. So every second, let's say two molecules evaporate. So two molecules they evaporated, and every second two molecules condense back again. So the amount of particles is still four. That means the amount is not changing. This is known as equilibrium. Equilibriums are only reached when the rate of forward reaction, the rate of backward reaction, they are equal. This is known as dynamic equilibrium. And the first thing they're going to ask you about is they're going to ask you about the definition of what a dynamic equilibrium is. So a dynamic equilibrium is when the rate of forward reaction, so when the rate of forward reaction equals the rate of backward reaction. In a reversible reaction. And this happens in closed systems. So why is the word dynamic used over here? The reason dynamic is used is because although there's no net change that's happening, the number of molecules, water vapors, they always remain 4. But the reaction, the evaporation process is happening and the condensation process both are going on, which means the reaction is still going on, but the end result is that the overall change, there is no overall change. Everything remains exactly the same. So, which is why the term dynamic is used. There's another type of equilibrium that you study in physics, which is a static equilibrium. In that, nothing is happening. I mean, over here, something is happening, but the net result is zero. As anyways, that's why dynamic is used. The word dynamic is used. The other thing about this is that it's always in a closed system because you never see water evaporating if you have a bottle of water and you have put a cap on it. The thing is, it's always evaporating, but it's also condensing at the same time. I mean, the molecules have nowhere to go. If the system was not closed, if this was open, all the water vapors would evaporate, and they would go out of the container. So they're never going to fall back into the liquid state over here at least. Maybe they might condense somewhere else. So which is why closed systems are important. Usman, exactly. ठीक है, in static equilibrium, nothing is happening. I mean, if यहाँ पे reaction चल रहा है ना, ठीक है, in static equilibrium, literally nothing is happening. ठीक है, for example, there's a book on a table. It's in equilibrium, but it's static equilibrium is more of a physics concept. All the forces are canceling out, and there's literally nothing happening. I mean, the book is just stationary, and the table on which it's kept, it's also stationary. As anyways, uh, let me add a border to this. 1 second. So now I'm going to move towards Le Chatelier principle. Le Chatelier principle is so what's the Le Chatelier principle? Le Chatelier principle is that the equilibrium opposes any change that's introduced to the system. So the principle simply states that your equilibrium, okay, and we're going to keep talking about this equilibrium because this is the simplest equilibrium. It's easy to visualize as well. So equilibrium opposes any change that's introduced to the system. That is introduced. So whatever you're going to try and do, the equilibrium is going to oppose that. Um, and after this point, we're going to ignore the Le Chatelier principle because the statement even is kind of confusing. We're just going to focus on the main points. I mean, what does the Le Chatelier principle state? What are the main points, which you have already studied in O levels? So the first point is number one: if you increase temperature, okay, this is more important. You can just remember the definition. If you increase temperature, what's going to happen? If you increase temperature, endothermic reaction is favored. Is favored. Okay, that's the first point of Le Chatelier principle, and we can apply this point over here in this equilibrium. What's going to happen to this container if I start heating this? If I increase temperature, if I apply heat, what would happen? I mean, the two reactions going on. Let's assume that the two reactions are happening at the same speed. There's forward reaction happening and backward reaction happening, and they're happening at the same speed. It's an equilibrium. But as soon as you start applying heat, then one of the reaction would actually become faster, which is, I mean, more evaporation would happen. So that means every second now, instead of, let's say, 3 molecules evaporating, now there are 4 molecules evaporating. And every second, instead of 3 molecules condensing, now just 2 molecules are condensing. So if this keeps going on, every second 3 molecules, 4 molecules evaporate, and just 2 molecules condense back. That means the net quantity of vapors are going to keep on increasing. So the equilibrium is going to favor one of the side. Okay? And the equilibrium is going to favor the endothermic reaction. The endothermic reaction is going to speed up. Evaporation is an endothermic reaction. Okay? So in the example above, we can write this in the example above. Evaporation, which is the endothermic reaction, is favored. And remember, I'm using the word favored, okay, for a reason. Um, because we're not talking about the rate of the reaction. We're actually talking about the relative speed of the two reactions, forward and backward. We're not talking about the rate, but the relative speed. Relative speed means, I mean, you're talking about rate, but the relative rate, which means, I mean, there are chances that both reactions would slow down. But when I say one of the reactions is favored, that means one of the reactions is faster compared to the other one. The evaporation, Rida, evaporation is when, how does evaporation happen? You have this molecule. Okay, let me pick this molecule. This is a liquid molecule, right? This one over here. So this molecule has to gain energy. It has to become energetic, and only then would this molecule evaporate. Okay, but it has to become energetic to evaporate. So it's going to gain energy. So evaporation is an endothermic process. Rida, is this clear? Acha, this could be slightly confusing. Uh, and let me, okay, Rida, I get your point, but it's a slightly confusing point. When we talk about endothermic, okay, let me clear this. When a reaction is endothermic, that means whatever particles you have in a reaction, they're the ones that are absorbing energy. So let's say you have these 5 particles and they're undergoing some reaction. So they're going to absorb energy from the surrounding, right? So energy in whatever form, light, etc., infrared, it's going to get absorbed if the reaction is endothermic. So the surrounding, the temperature is going to drop. Okay, so always remember, if if a particular reaction is endothermic, the surrounding temperature is going to drop. Now over here, what am I doing? I'm basically trying to increase temperature. What does the Lee-Chatelier principle state? It's going to oppose that change. So it's going to try and drop the temperature. So if I try to increase the temperature, if I try to provide it heat, it's going to try and decrease the temperature. Or we can keep things simple, which is just look for the whenever you increase temperature, the endothermic reaction which needs energy. If I'm giving it energy, the reaction that needs energy, that's obviously going to get favored. I mean, if I give it energy, molecules would become more energetic, and evaporation would obviously speed up because evaporation needs energy. Condensation doesn't need energy, so evaporation would definitely speed up. So let's, Reza, do you get the first point? So we're going to keep things a bit simple, okay? Just remember, you increase temperature, you give the equilibrium energy, and whenever you increase temperature, endothermic reaction, which needs energy, that's obviously going to it's going to speed up because it needed energy. So you're providing it energy by increasing temperature, then the endothermic reaction would it's obviously going to speed up. And in the above case, it's evaporation. Okay, is this clear to everyone? Okay, vice versa. what's going to happen if I decrease temperature? Let's say I put this container in a fridge, okay, and I'm decreasing the temperature. The temperature has dropped to 5 degrees centigrade. Acha, so decrease if I decrease temperature, then which reaction would be favored? The exothermic reaction, because I'm removing energy now. So exothermic reaction is favored. Now it's a relative comparison. If I stop, first thing, if I stop providing it energy, then obviously the evaporation would slow down. Less and less molecules would evaporate. But at the same time, the relative comparison is that the condensation would happen at a much faster rate because I'm removing energy. If I'm removing energy, I've put it in a fridge. These molecules over here that were very energetic and that were just buzzing around, okay, these gaseous particles, they would start to lose energy in a cold environment. And they would start, so now 6 molecules, let's say, condense every second, and 3 molecules, or the rate of evaporation is slower. Next second, 6 more molecules, they condense, and just 3 molecules, they evaporate. So eventually, what would happen is that the number of gaseous vapors would decrease. So exothermic reaction is favored, and we can write that in the above example. So in the above example, condensation would be favored. I said now, remember, it's very important. I'm again stressing on this fact that we're not talking about the rate of reaction. And I'm going to stress this point again, that if there's a reaction going on, reactants, there's a forward reaction, there's a there's a forward and a backward reaction. Just wait 1 second. The board is hanging up. I say you have a forward reaction happening and a backward reaction taking place. And uh, let's say I'm just going to 2 particles per second. Okay, let's say 2 particles. Let's call that 2p. 2 particles per second are changing into reactants, from reactants to products, and at the same time 2 particles, not even two. Let's make it 12. Okay, and at the same time 12 particles per second are changing back into reactants. So that means the reaction is at equilibrium because the rate of forward and the rate of backward reaction are equal. Now, the reason I'm stressing about using the word favored instead of actually mentioning the speed is that in O levels you studied that if you decrease temperature, right? If you decrease temperature, then particles become less energetic, and if they become less energetic, so I can write that you have less energetic. So you have less energetic particles. 1 second. ठीक है, Bazika, just after this point, I'll just give you a brief overview. ठीक है. So right now, 12 particles are changing into products, and at the same time, 12 particles from the products are changing back into reactants. Now, if you decrease temperature, in O levels, you studied that the particles become less energetic. So you have less frequent and effective collisions. I mean, the rate of reaction will be slower. So your reactions are going to be slower. So less frequent and less effective collisions, and there's going to be slower rate, or the speed of the reaction will be slower. So if I decrease temperature, think of this as the equilibrium. Think of this as liquid water evaporating and condensing at the same time. So So think of this. What would happen if you decrease temperature? So instead of 12 particles changing from reactants to products, the speed would decrease. And it's not just the forward or the backward, both reactions, their speed would decrease. So instead of 12 particles changing from reactants to products, the number of particles might decrease to 6. Right? Both reactions would decrease in speed. But we can just one second. Let's keep that at 12. But we can also bring in this endothermic exothermic part. So let's say one of the reaction is endothermic and the backward reaction is exothermic. When you decrease temperature, according to the equilibrium or the laws of equilibrium, according to the laws of equilibrium, if you decrease temperature, which reaction should be favored? Exothermic should be favored. So exothermic reactions, they are the ones that are going to be favored. Just wait one second. The board is hanging again. Okay, now it's there. So exothermic reactions should be favored. Now, now very carefully, this point is slightly trickier. Don't confuse rate of reaction with this thing. Okay, you're decreasing temperature, both reactions would slow down. So whenever you decrease temperature, both reactions would slow down. Let's decrease the speed to 6 particles per second. 6 particles per second changing from reactants to products. And at the same time, 6 particles per second are changing from products to reactants. But then equilibrium states that the exothermic reaction is favored. That means the speed of the exothermic reaction would actually be slightly greater compared to both reactions are slowing down, but the exothermic reaction might be slightly faster compared to might be slightly faster. Okay. I'm restating my point, which is that don't confuse the speed of the reaction with what the equilibrium is stating. Okay. Equilibrium uses the word favored, it doesn't use the word speed. What you mean by favored is that one of the reaction would be slightly faster compared to the other reaction. It doesn't mean that the reaction would actually be faster. For example, in this case, if you decrease temperature, in this particular case, if you decrease temperature, the exothermic reaction is favored. That just means that the exothermic reaction would be slightly faster compared to the endothermic reaction. It doesn't mean that it's actually going to be faster in absolute terms. But initially, it was actually fast. It was 12 particles per second. This was 12 particles per second. They're both actually slowing down. Whenever you decrease temperature, the rate of the reactions or the concept of rate of reaction suggests that the particles have less energy, so they're going to be less frequent and effective collisions. So rate of reaction would be slower. So both reactions are actually going to be slower. But one of the reaction, according to Le-Chatelier principle, would still be faster compared to the other one. So remember this point. Never use the word speed over here. Okay? When you say that one reaction is faster than the other one, it's just a relative comparison. Maybe both reactions are speeding up. Maybe both reactions are slowing down. So it's always a relative comparison. I mean, we can do the opposite. Okay, let me explain what the opposite would look like. What if I increase temperature? So if I increase temperature, what's going to happen then? If I increase temperature, and I'm going to write it over here. So if I increase temperature, um, rate of reaction suggests, I mean, rate is going to increase. The rate of reaction is going to increase because if you increase temperature, the particles have more energy and they're going to be more frequent and effective collisions. So both forward and backward reaction speeds are going to increase. So let's say I'm increasing temperature. So now 15 particles per second are changing into products and 15 particles per second are changing back into reactants. So let's assume that I've increased temperature and the rate of both reactions would kind of increase. Forward and backward both would increase. But equilibrium suggests that one of them, I mean, they're not going to increase equally. One of them would actually be faster compared to the other one. So equilibrium is going to suggest or what does the Lee-Chatelier principle suggest? That if you increase temperature, the endothermic reaction would actually be faster. So that means the endothermic reaction would actually be slightly faster compared to the other reaction. So I've made that into 18 particles per second. So never ever confuse the equilibrium concept with the rate of reaction concept. Okay? Always use the word favored. Uh, because whenever you decrease temperature, both reactions would slow down. But when you say that the exothermic reaction is favored, it means that both reactions are slowing down, but the exothermic reaction is still relatively faster compared to the endothermic reaction. And whenever you increase temperature, rate of reaction suggests that both reactions would speed up. But equilibrium is going to suggest that the endothermic reaction would still be faster compared to the exothermic reaction. Hopefully, is this point clear? Yes or no? Is this point clear? Rida, Heba, is this point clear? Sanjida? Achha, so just 1 second. ठीक है. So remember, I'm going to write this. The reason I'm stressing this point over and over again is because in the question, a lot of times what they're going to do is they'll be asking about equilibrium, and all of a sudden they're going to start asking about rate of reaction. Okay? So so I mean, if you look at this reaction, the question would come like this: that they would be asking about what's going to happen if you increase temperature, and where would the equilibrium shift? Now he's talking about equilibrium, and you're going to suggest that if you increase temperature, the endothermic reaction would be favored, so forward would speed up, right? And all of a sudden, he's going to suggest what's going to happen to the rate of the backward reaction. Now, the rate of the backward reaction would also speed up because whenever you increase temperature, both reactions, irrespective whether it's forward or backward, both reactions are going to speed up. So we're going to do a few questions on this. Just 1 second. Uh, and let me highlight this as an important point, which is don't confuse equilibrium with rate. If the equilibrium suggests one of the reactions is speeding up, or sorry, is being favored, it doesn't mean it's actually speeding up. It just means that it's faster compared to the other one. So don't confuse equilibrium with rate. As anyways, the board is still glitching. Uh, now it's written. Uh, so let's do a question on this. Now, how would an actual question? I mean, you got a lot of questions like the Haber process. All of them are gases. So let's get that out of the way. The enthalpy change of this reaction is given as minus 88 kilojoules per mole. Now, this question over here, you have this is how the equation would appear. Now, you're not going to be given that the forward is endo or the backward is exo. This would not be written over here. You're going to look at the enthalpy change. When you look at the enthalpy change is always for the forward reaction. It's always given for the forward reaction, which is this one over here. And it's given as minus 88. So that means the forward reaction is the one that's exothermic. Okay, so it's not going to be written in the equation. You have to look at the enthalpy change. The enthalpy change is always provided for the forward reaction, so that's exothermic. The backward is going to be exactly the opposite. So if the backward is not given, it's going to be the opposite. So it's going to be endothermic. So if the forward is minus 88, then the backward would be plus 88. So you'll get that. Now the question is, you're decreasing temperature. So the question is decreasing temperature. And which reaction is favored? That's the question. Uh, and the equilibrium would favor which reaction? Now, if you decrease temperature, equilibrium is going to favor the endothermic reaction. Need not the endothermic reaction. The rule is if you decrease temperature, equilibrium favors the exothermic reaction. Now, the exothermic reaction in this case is the top one. Okay, so every time you have to check which one is the exothermic reaction. The rule is decreasing temperature, equilibrium favors exothermic reaction, which in this case is the forward reaction. So that means the forward reaction would be favored. So that's about equilibrium. But simultaneously, you might be asked about rate. I mean, you might be asked that you're decreasing temperature. So what happens to the rate of forward reaction? Now, this question is not about equilibrium. What happens to the rate of forward reaction? So now, so when the question is stated like this and he's talking about the rate of the reaction, then ignore equilibrium. Rate of reaction, whenever you decrease temperature, molecules become less energetic and the rate of the reaction decreases. It decreases irrespective of the fact whether it's the forward reaction or the backward reaction. Every reaction, the rate would decrease. So you're going to state that the rate decreases. Okay, what the equilibrium is simply suggesting is that the forward reaction, even though both reactions, the decreasing temperature, both reactions would decrease in speed, but the forward reaction would still be slightly faster compared to the backward. Okay, is this question clear to everyone? Yes or no? Is this clear? So just a quick recap about this. Bazaka, we were doing, I mean, we did temperature and we did dynamic equilibrium, and we were talking about this whole equilibrium where you had liquid water in equilibrium with gaseous water molecules. So the rate of forward reaction and the rate of backward reaction was equal. Like if 10 molecules evaporate, but at the same time 10 molecules condense back again, so the net result would be that there would be no change in the amount of water vapors and the amount of liquid water over here. So that's dynamic equilibrium. Rate of forward equals the rate of backward reaction. And then we started studying the Chatelier principle, and we studied the first rule, which is if I start increasing temperature, then in this equilibrium, if I start heating this up, okay, I put it on a fire, on a stove, and I start heating this container that has liquid water, then obviously more water molecules are going to evaporate. Uh, so the rule is if you increase temperature, endothermic reactions are going to speed up because they need energy. Endothermic reactions are the ones that need energy. So if you increase temperature, then those reactions that need energy, they're obviously going to speed up. So there's going to be more evaporation that's going to take place. You get more water molecules are going to be produced. Then are going to, so every second, let's say 10 molecules would evaporate, and every second only 5 would condense back. If you're increasing temperature, the rate of evaporation would be faster. Okay, Bazga, is this clear?
Yes, sir.
Or vice versa, if I decrease temperature, if I put this container in a fridge, in a refrigerator, then automatically refrigerator क्या करता है? It removes heat energy. So these gaseous steam molecules that were energetic, they're going to start losing energy, and they're going to start condensing back again. ठीक है, because they're going to lose energy in a cold environment. So अब उल्टा हो जाएगा. The exothermic reaction is going to be favored. These molecules, they're going to start losing energy, and which means exothermic. So exothermic reaction would be favored if you decrease temperatures. These are the two rules that we studied. That increased temperature favors endothermic reactions. So simple rule, Le Chatelier principle, and decreased temperature favors exothermic. And then I stated this particular idea that always remember, always check whether he's asking for equilibrium or whether is he talking about rate of reaction. Okay? So remember, if ever he's talking about decreasing temperature and he's all of a sudden talking about rate of reaction, then the rate of reaction, whether it's the forward or the backward, both reactions, their rate would decrease, irrespective of whether they are endothermic or exothermic. Both reactions, the speed would decrease if you decrease temperature. And if you increase temperature, rate would increase, irrespective of the fact whether it's the forward or the backward. Both reactions, their rate would increase. What equilibrium suggests is that one of the reaction would be faster and one of the reaction would be relatively slower. So both of the reactions could decrease in speed, but still one of the reaction would still be faster compared to the other one. So that which one is favored, which one is faster compared to the other one can be determined by these 2 points. Okay. Achha, do we have any questions about this? Sanjida, is this clear? Rida, Hiba, everyone, is this clear? Okay. We're going to cover the Lee Shatler principle, then we continue tomorrow with this. Make sure I've given you assignments over there. I've given you playlists for those as well. Uh, energetics, can I try and complete all the energetics questions and see if you have any problems with energetic questions? Apart from drawing hair cycle, that's tough. The other questions are relatively very simple. MC delta T, the formulas, formation minus product minus reactants. So try and do as much. You won't have time at the end. Okay? You have to do all these questions right now. I mean, May June is going to come very quickly. Okay? You don't have time. You don't have a lot of time. Okay? So practice as many questions on energetics. All the worksheets that I sent. Try and complete all of them. Okay? So okay, take care. Allah Hafiz.